All right. Good evening, everyone, and welcome to the Pease RAB meeting of 28 February pre-recorded videos. So for new members attending, and for those that may not know me yet, I'm Chris King. I am the Air Force Program Manager for Pease, and I am tasked with managing the remedial efforts from past Air Force activities at Pease. With me today are fellow members of the Air Force team, your community RAB co-chair, Ms. Andrea Miko, our remedial investigation consultants from Wood, Mike Daly from the EPA, and Peter Sandin from the New Hampshire Department of Environmental Services. We are trying a new format for this February RAB meeting, making use of this pre-recorded video segment. I will start by giving a short update on the status of the PFAS remedial investigation efforts to date and present some exciting new guidance documents issued recently by the DoD. From there, I'll pass the mic over to Mr. Hank Andelzik and Ms. Amy Quinton from Wood to present the validated RI remedial investigation, groundwater results to date, and the backyard produce results conducted last year. As you can see, this will be our agenda come the 28th when we have our full RAB meeting. Okay, this video will be played at the beginning of the RAB meeting held on February 28th. Following the playing of this video, we will conduct some RAB administrative business, meet the new RAB members, and get an update from the City of Portsmouth before we have our regular RAB question and answer discussions with the community. At that time, the RAB is encouraged to ask any questions related to the content of these videos. Later in the meeting, we will allow members of the community to submit public comments before adjourning. The public comment process will be discussed at the start of the Q&A session on the 28th. All right, next slide, please. Go back to the previous one, my apologies. So just to give a quick update on the status of the remedial investigation, we will present to you today what is essentially the phase 1 results. Phase 1 started in May 2021 and ended this winter before Christmas. Our consultants from Wood led the field work and collected over 2,600 individual samples and drilled 76 new wells around Former Pease. The groundwater and produce data from this phase 1 effort are the subject of this RAB meeting and will be presented here shortly. This has been a massive effort to date, and going forward, we are looking to a lot more of the same. So we want to thank all of the community members that have given property access for sample collection and have participated in this RAB so far. All right, next slide. All right, some good news. The DoD recently issued a guidance document conveniently called Guidance on Using State Per and Perfluoroalkyl Substances in Drinking Water Standards in Circular Removal Actions. So what this essentially does is this allows the DoD to consider state, not only New Hampshire, but other states' ambient groundwater quality standards when addressing private wells. This was not the case before. We were focused mainly on the EPA Lifetime Health Advisory limits. And so now we're allowed, not necessarily forced, to address state levels. Okay. What this means is that certain wells at private residences can now be connected to city water or install, public or point of use treatment systems. We're hoping to get some guidance from the Air Force, which is under development as well. Obviously, from the DoD, it goes to the individual services. And once we receive some guidance from the Air Force, we can start contacting potentially impacted residents. What this really means is that the DoD is engaged and they are putting out these new guidance. And this is really a huge win, not only for the local community around Pease, but any other DoD impacted facilities. So great news. Going forward, this is the start of hopefully a lot of good news to come. All right, next slide, please. Okay, right now we're talking about the remedial investigation. Essentially, this isn't the start of all these efforts. This started many years ago when they started doing, the baseline characterization of the sites. But we're in the remedial investigation right now, where we're looking at characterizing the site conditions to determine the nature and extent of contamination from historical releases. And we're also, during this phase, evaluating potential and current future risks to human health and the environment based on exposures. When we're done with this, we move into the feasibility study, and that'll be starting around right after the report is done in June 2023. So in that effort and the feasibility study, we will look to ensure that the appropriate remedial alternatives are developed and evaluated, and so that information can be presented to decision makers to make the proper decision for the future of Pease. And following some public comment period, there will be a record of decision where we talk about remediation going forward. Okay, so next slide, please. All right, so this is an iterative process, and from now, I will turn this over to Hank Andelzik, and he will present to you the groundwater results to date from this phase 1 effort. All right, thank you.
Thanks, Chris. I'm Hank Andolsik. I'm a project hydrogeologist with Wood. And before I get started sharing the various groundwater maps we've compiled, I just want to introduce some nomenclature that I'll be using in my presentation. For those who might be first-time attendees, I'll start with a general introduction of the geology that comprises the former base and peninsula. It's important to understand that although I'll be showing you maps that appear to be in 2 dimensions, they provide data that also includes a 3rd dimension. The geology across the peninsula plays a significant role in how groundwater contamination spreads laterally as well as vertically. To begin with, the slide on the left is a cross-section of a glacial deposit typical of what you might see across the peninsula in the unconsolidated sediment deposits, also referred to in this presentation as the overburden. The clay, silt, sand, gravel, and cobbles that have been deposited were done so by the advancing and receding glacier. The rate at which water can move through the overburden is somewhat dependent on the grain size of the deposit. In other words, water tends to move more easily in cobbly deposits than it does in silty deposits. The image on the right is bedrock and typical of what you might see beneath the overburden. You can see in the image a series of vertical and horizontal breaks in the rock. Those breaks, called fractures, are how water moves through the bedrock. The rate at which the water moves through the fractures is somewhat dependent on their aperture, which is the size of their opening, and their interconnectedness. Next slide, please. This slide is another example of the movement of groundwater through various layers that make up the geostratigraphy across the peninsula. The sponge is an example of how water moves through the overburden. The sponge has many interconnected pores of various sizes. When you soak a sponge, you know it holds a lot of water. Similarly, the overburden holds the volumetric bulk of the water in the aquifer because of its high porosity and interconnectedness. The solid block of wood in the middle is analogous to bedrock. If it isn't fractured, there isn't much water in it. However, if you break the block of wood, like on the far right image, water can occupy the fractures. But as you can see from these drawings, that for the same volume of material, the sponge, or in reality, the overburden, holds much more water than the corresponding volume of fractured bedrock. Next slide, please. Here's an example of a generalized cross-section of the peninsula. The overburden deposits consist of the upper sand, the marine clay silt, and the lower sand. As suggested by their names, these are deposits of unconsolidated sediment. Beneath the overburden is the bedrock. In the top 10 to 20 feet of bedrock is referred to as the fractured bedrock, which is denoted by the light gray below the lower sand. This top layer of bedrock is generally highly fractured, so much so that it behaves hydraulically much like the overlying sediment deposits. Beneath the fractured bedrock is a more competent, less fractured bedrock. We refer to this as either the deep bedrock or just bedrock. And for water to be present in the bedrock, there needs to be fractures. All of these layers contain groundwater as depicted by the blue lines. Water flows with relative ease through all the layers except the marine clay silt and unfractured bedrock. The marine clay silt is not continuous across the peninsula, and where it is absent, the upper sand and lower sand are joined, and that unit is generally referred to as the upper sand. Where the upper sand is eroded, like along the western side of the peninsula, where you have an escarpment, groundwater is exposed at the surface along the contact between the upper sand and the marine clay silt, also shown on the image, where the arrow is pointing to the springs. Where this occurs, there tends to be the formation of seeps or springs. Springs are simply groundwater seeps that are flowing. Peverly Brook, Knightsbrook, Pickering Brook, all originate from springs along the upper sand marine clay silt contact. Next slide, please. In these images, you can see what the actual soil looks like beneath the peninsula, from the shallowest on the left to the deepest on the right. The left image is that of the upper sand. A little deeper, the middle image shows you what the marine clay silt looks like. And deeper still, the image on the right shows the transition between the lower sand at the top of the image and the fractured bedrock at the bottom of the image. Next slide, please. Now that you've got a basic understanding of the geology, I'm going to move on to discussing the groundwater maps. First, I'll walk you through the symbology that appears on the box plot and dot plot maps I'm going to be showing you. Just to orient you, north is to the top on all the maps that I'll be showing. What you see here is a box plot map on the left. These box plot maps were produced as an alternative to what is known as chembox figures. A chembox figure shows the location of the sample, then as a small spreadsheet with the sample results next to the sample location. The problem with chembox figures for this project is that there are hundreds of samples that have been collected across a very large area. Chemboxes would simply be unreadable, and box plots allow you to quickly see, based on color, the distribution of contaminants across a large area. When we get the RI report produced, there will be accompanying tables to complement these figures that will provide specific values for each sample collected. So on the left side of the slide is an example of the PFAS distribution in the lower sand aquifer. The L to the left of the boxes denote lower sand, and the key to the lithologic symbol is in the box on the right side of the slide. The 5 colored boxes in a row on the left side of the slide represent the 5 compounds shown at the top right side of the slide in that order. So the first box is always PFBS, and the last box is always PFNA. These compounds were selected because New Hampshire has an ambient groundwater quality standard, AGQS, for 4 of them: PFOS, PFOA, PFHXS, and PFNA. And PFBS has a risk screening level, an RSL, for groundwater. These guidance values are shown beneath the listed contaminant at the top of the right side of the slide. Their values are nanograms per liter, also referred to as parts per trillion, or PPT. The color coding of the boxes reflect the general concentration of the compound specific to that box. White means it is non-detect. Green means it is detected, but was below the corresponding guidance value. Orange indicates it is above the guidance value, and red indicates it is 10 times greater than the guidance value. Next slide, please. The other type of map that I'm going to be showing you is what we call the dot plot map. The color coding is similar to the box plot maps, as are the contaminants displayed. However, these maps are contaminant specific. This map shown to the right of the slide is the PFOS distribution in overburden groundwater. They're difficult to see on this slide, but there are a series of dots along the west side of the peninsula that have blue halos, and I'll show you this later too. Those points represent springs or seeps that were sampled. So anything with a blue halo is a spring or a seep. I mentioned previously in the general geology introduction slide that we consider the fractured bedrock to be similar hydraulically to that of the upper and lower sand deposits. So on this map, we have combined the geologic layers into just 2 layers: the overburden, which includes the upper sand, lower sand, and fractured bedrock, and the bedrock, which is all the bedrock deeper than the fractured bedrock. Unlike the box plots, which show concentrations of the 5 target contaminants across a specific horizon, the dot plot maps show specific contaminants across hydraulically similar layers. Although not shown in this example, I'll also be showing you preliminary concentration contours of specific contaminants with respect to the guidance values, which are shown at the top right of the slide. All right, so at this point, I'm going to begin with sharing my screen and begin with the box plot maps. Okay, I think Amy needs to stop sharing. All right, can everybody see that?
Yep.
Yes.
Okay, thank you. Okay, I'm going to begin with the box plot map that will show you what the concentrations of the 5 compounds I mentioned earlier, PFBS, PFOS, PFOA, PFHXS, and PFNA, look like at each sampling location. The data presented on this map are inclusive of all groundwater samples, all validated groundwater samples collected thus far as part of the remedial investigation, including samples collected during the base-wide and Site 8 site inspections, the expanded site inspection, and the routine sampling collected as part of the Site 8 and AIMS performance monitoring plan. The black dashed line is the Pease Development Authority property boundary. And I'm going to begin with turning on the potentiometric surface, which is a contour surface of the underlying groundwater across the peninsula. The high point for groundwater on the peninsula is at Site 8, which is up here. The former fire training area, where much of the AFFF was used. The blue lines are called equipotential lines, and groundwater flows perpendicular to those lines. So I'm just going to draw on here to move some things here. Did I stop sharing?
Yes, you did.
Sorry, it's blocking my sorry about that. I'm trying to get access to part of my screen. Here we go. All right, so I'm going to draw some I got to find my okay, I lost my cursor. So if rain drops right here, it's going to flow perpendicular to these lines. So it's heading down in this way. This is where groundwater moves. So it's also going in this direction. So it's running groundwater. These flow lines, or groundwater flow lines, are running essentially perpendicular to these equipotential lines. And so you can see here is that the source area is up here at Site 8, and as a result of it being the high point of the peninsula, there's radial groundwater flow from that area, which caused widespread distribution of the contaminants. All right, I have to move this back over so I can grab my hand. All right. Next, I'm going to show you the distribution of the 5 compounds in the overburden, which consists of the upper sand, lower sand, and fractured bedrock. And I'm gonna zoom out a little bit to make sure that we have the full domain of samples collected. And we have the one down there. And you can see it's a bit messy. As I zoom in, there you get separation between the boxes. So during the Q&A portion of this presentation, you know, if you have specific questions about that, I can zoom into certain areas, and we can resolve the sample locations much better. But you can see the L and the F that indicates, you know, lower sand, fractured bedrock, and so on. So I'm going to just turn this layer off. And so I have the upper sand, the lower sand, the fractured bedrock, and the seeps, which all comprise the overburden. So I'll turn off these layers, and I'm going to turn on the bedrock, the deep bedrock. And this is what the deep bedrock looks like. And what you can see here is that the first box, which represents PFBS, as I mentioned earlier, is mostly white or green across this area. And the last box, which is PFNA, is mostly white, indicating non-detect. Most of the exceedances, the AGQS exceedances, are associated with PFOS, PFOA, and PFHXS. Now I'll show you what the map looks like with all the layers turned on. And this gets really busy. I know it's difficult to comprehend what's going on at the scale, but again, during the Q&A, I'll be able to move around, and I'll just give you an example. I'll just zoom in quickly here, so you can see how the separation occurs as you get closer to this data. So we can talk about it in more detail during the Q&A. So now I'm going to move on to the dot plot map. Here again, you see the PEA boundary, as well as the locations of the Haven, Harrison, Smith, Portsmouth, and Collins wells. I can turn on the groundwater contour map, but I'm going to leave it off for now because this map will get very busy very quickly. On this map, as mentioned previously, the upper sand, seeps, lower sand, and fractured bedrock are all lumped together and called the overburden. I'll begin with the distribution of PFOS in the overburden. There we go. As I mentioned previously, the circles along the west side of the flight line with blue halos around them are seeps and or springs. So this, I'll see if I can zoom in, but I think it's gonna make the dot smaller, but we'll see. Where you can see there's some here and there. So I'm going to zoom back out, and I'm going to zoom out so we can see the full scale of the samples collected. And make sure there's nothing to the south. Nope, just that one right there. So that's pretty much the full domain. Back it out one more time. Okay, so that's the full domain. Now I'll toggle through the contaminant specific dot plots. Next will be PFOA in overburden. So I'll turn this off, turn off PFOS, and turn on PFOA. And I'm going to toggle back and show you there's not a whole lot of difference. So that's PFOA. And that's PFOS right there. So not a whole lot of difference between the distributions. So back to PFOA in overburden. Now I'm going to look at, I'll show you PFHXS. And this is PFHXS. PFBS, there'll be a big change here. And lastly, PFNA. So I'm going to turn off the overburden layer for a bit and move on to the bedrock layer. So I'm going to turn off the PFNA, turn off that layer, and begin showing you what the bedrock looks like. And I'm going to start with PFOS in the bedrock. And PFOA. PFHXS. PFBS. And PFNA. So I'm going to turn the bedrock layers and I'm going to turn all the layers on just so you can see. And this is essentially, when I do this, it'll be essentially similar, very similar to what the box plots showed. Oops, not that one. I think I have everything on. Okay, so now I'm going to turn off the bedrock layer. And I'm going to turn off, I'm going to leave the PFOS layer on. What I'm going to do now is I'm going to show you concentration contours for PFOS detected in the overburden. So similar to the dot plots, the red lines mean that the samples within the polygon. So I'm going to zoom in a bit here. So the red lines means that samples within the polygons are 10 times the AGQS for PFOS. Samples within the orange polygons are above the AGQS, and samples within the green polygons are below the AGQS. So basically those are kind of trace levels. Anything outside the orange and inside the green is trace, and beyond the green is non-detect. So I'm going to turn off this green contour line just to keep it, just for housekeeping. It's a little busy. And I'm going to turn on groundwater contours. I'll turn on the groundwater contours. Well, actually, before I do that, I'm going to explain too about these what appear to be disconnected blobs. I want to point them out. They are not necessarily, so you have a bunch here and here. They are not necessarily the result of additional source areas. What is shown here is one way to interpret the data. As I previously mentioned, these contours are preliminary. At this time, we chose not to connect the outlying blobs. That's just for lack of a better name to call them, with the main core of the plume. However, you could connect them in some areas, and I'll just do that right now. I'm going to zoom in a little bit. And I don't have orange in my color palette here, but I have yellow. So we're going to have to pretend that my yellow is orange. All right, so I need to turn on the groundwater contours for this. So it's going to get busy again. And so if I was going to connect this, I connected something like this, and that would connect onto that yellow or that orange main portion of the core of the plume, and that would come up, kind of come up like that. So you connect them like flow lines. So you try to draw them as perpendicular as you can to the equipotential lines. So that's how it would look if you connected them. So we chose not to connect them, these blobs of contamination, because our focus at the moment is the leading edge of contamination. So, here, 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 and so on, because groundwater is moving in this direction, in that direction, and in this direction. as that poses the greatest risk to the potential receptors. Furthermore, the heterogeneity exhibited in the hydrogeology and at times in the sampling data, and the episodic nature of the application of AFFF, which is the primary source of PFAS contamination here, further support this is a reasonable interpretation. I need to emphasize that these maps are dynamic and that they will be revised again as more data is collected. So I'm just going to clean up. I got to find my eraser underneath this. Here it is. And clean this up a bit. And grab my hand. All right. So now I'm going to turn off all the dots, but turn on the red and orange contours for the 5 PFAS compounds in the overburden, so you can see the interpreted distribution. So this is, well, let me back up again. This is I'll zoom out so we can see the full extent here. And I actually missed something, didn't I? All right. Get the full extent. All right, and there is one point really far south, but I'm not gonna, maybe I will include it. And I'm gonna turn off the contours because it's really too busy with those on. Okay, so that's the PFAS distribution. And that is the contours, and I need to get the data turned off. So there. So that's PFAS contours. I'm going to do the same thing for PFOA. That's PFOA. And let's turn that off and let's look at PFHXS. That's PFHXS. And let's look at PFBS. And lastly, let's look at PFNA. All right, so now I'm going to turn on all of the overburden contours. Get a sense of, now you can see somebody's on green. I don't know. Right. We'll figure that out in a minute here. Right there. Still have somebody turned on here. That's it right there. All right, so no green on, just orange and red. All right, so now I'm going to turn off the overburden and I'm going to turn on the bedrock, and this is the contours here. Let's look at the contours and turn that off. Hang on a second, I got too many things turned on here. It's a very busy map. All right. So that's PFAS. This is PFOA. PFHXS. PFBS. Not a lot going on there. And PFNA. And again, I'll turn on all the layers now, all the contaminants, not layers, all the contaminants in the bedrock. And that gives you a sense of what's happening in the bedrock. So now I'm going to go back up and leave this on, and I'm going to turn on the overburden. And as you can see, how the distribution of the contaminants in the bedrock fall within that of the overburden. This is important because it suggests that the bedrock, at least at this scale, behaves similarly from a hydrogeologic standpoint to that of the overburden. This ends the presentation on the distribution of PFAS compounds in groundwater, and any questions you may have can be answered during the Q&A portion of this presentation. Thank you.
Thanks, Hank. I will reshare my screen and quickly introduce myself. My name is Amy Clinton, and I'm a human health risk assessor. And I'm going to be presenting today on the backyard produce sampling. So let's just get my slides back up. Go. Be seeing the slides show where we left off earlier. And we'll advance it. So I'm going to start by talking about the migration pathways. So how contamination of PFAS from peas could potentially move into backyard produce and pasture grass. And then I will talk about the sampling program that we implemented to evaluate this exposure pathway. And then I will talk about the results that we have received. So we know that peas there's groundwater associated with peas that has PFAS in it that is moving off-site. This groundwater can be extracted by private wells, in some cases as drinking water, but in other cases as both drinking water or irrigation water, or in some cases only irrigation water. And from that water, it can be transferred to gardens. So we could see it potentially in soil of gardens, and there was the possibility that it could be taken up into fruits and vegetables. So the first part of the sampling program is attempting to evaluate whether or not that migration pathway exists and whether or not PFAS could potentially be coming into the human health food chain, essentially through the eating of vegetables that have been exposed to PFAS. And the second part of this sampling event, we're looking into the possibility of cattle being exposed and then people being exposed from potentially eating this beef cattle. So there's an extra step in this potential PFAS migration pathway. So we know again that peas has groundwater associated with it that has PFAS detected. In the farming scenario, it's not necessarily, although in some cases the cattle may also be drinking the water, but that's not what we're evaluating in this scenario. What we're evaluating is that this groundwater can become very shallow. And as Hank was previously talking about, there's areas where the groundwater comes to the surface is either springs or seeps. There's a lot of like wet land, wet areas around peas. And there's also something that we call hydric soil. So hydric soil is basically this poorly drained areas that tend to maybe flood out seasonally. They don't drain well. They may hold water for periods of the year, and where basically the groundwater is very, very shallow in these areas. So the potential is that PFAS can migrate from the shallow groundwater into this hydric soil, and there it could potentially be taken up by grass, eaten by cattle, which are then eaten by people. So these are the migration pathways that we attempted to evaluate. So looking at this figure on the left-hand side, we sent questionnaires out to this northern portion above the base and also to this western portion to try to identify properties where residents were essentially were extracting groundwater in private wells that were used for irrigation. And many of these residents are residents that we already know have private wells, are already in our drinking water system. In those cases, it was a questionnaire designed to identify what other uses they're using for that groundwater. Are they using it to water fruits and vegetables? In which case, if we already have data for it, we could sample, we could look at the data and say, well, if there's PFAS in it, then that's a potential home that we might like to sample fruits and vegetables at. If it's a home that they have irrigation water and we didn't have a recent sample, then we were requested to sample that water to see if PFAS was recently detected. So out of that questionnaire process, we identified about 16 homes that had PFAS recently detected in the groundwater that they were using to irrigate fruits and vegetables. So we asked for sampling permission to go to these homes and sample their fruits and vegetables. And out of those, we received permission for 11 properties that have fruits and vegetables. We sampled a total of 12 properties, and that includes 3 farms, one of which did not have fruits and vegetables. And that's how that selection process was made. Within that sampling program, we sampled a range of fruits and vegetables at each home. We aimed for around 3, but it depends. Backyard gardens tend to be very variable. You have very avid gardens that have many types of fruits and vegetables. And then you have more, let's say backyard gardeners who have perhaps a bit less success in their gardens and only had a smaller number. But we'll talk about what we actually found and what we were able to sample in a couple of slides. But this is just to give you an overview of how we made that selection process. And so looking at the farms, for a couple of the farms, we already had some information to suggest that PFAS was moving through the shallow groundwater and potentially into hydric soils on the property. And for another farm, we had some upgradient results that suggested that that was a possibility. So that's how we screened in that information. And again, it was very much in discussion with the property owners and finding out how they're using their property and what their willingness was to allow us to sample. And so as part of the sampling program for the backyard gardens, we not only collected fruits and vegetable samples, but we sampled again that irrigation water so that we could have a current timestamp of exactly what was detected at the time of the sampling. And we also sampled a representative soil sample from each of the gardens. With the farm sampling, we collected multiple pasture grass samples from each of the 3 farms. And with that, we collected at least one, and in some cases more than one, hydric soil sample, which was paired with a very shallow groundwater sample. And in some cases, we also sampled sediment and surface water if that was relevant in those particular farms. And so just again, those green areas that are shown here are where the properties ended up that we were able to sample. And given that, the extensive effort that we made to send these questionnaires out, and to contact and follow up with properties that we thought might be impacted, we feel it's a fairly representative cross section, and in fact, probably a large percentage of the homes that are actually potentially impacted were sampled in the sampling event. So here's just an overview, and we'll talk about a little bit more of the specifics. But so for the fruits and vegetables, we saw absolutely no detected PFAS in any of the fruit or vegetable samples. So as we said, the PFAS was detected in the water. So we know that the irrigation water did have PFAS in it. And in about half of the cases, we saw some soil detection. It was mostly PFOS only and at very low concentrations. So we were seeing definitely in the water, possibly, and in some cases in the soil, but none of that was transferring into consumable fruits and vegetables. So at this time, based on the sampling round, there's no concern at all for uptake of PFAS into fruits and vegetables by this pathway. And then looking at pasture grass, we saw no PFOS and PFOA and no PFBS. So essentially none of the chemicals that we have toxicity values for were taken up in the hydric soils. And there was very little uptake at all. We'll talk about a few more details about that. There were 2 PFAS chemicals. However, it was very low frequency of detection and very low levels. And none of that was in active pasture areas. So again, the outcome of this, based on this data, is that there's no concern for eating beef cattle that are grazing on these grasses. So here's a little more detail on what we were able to collect in this fruit and vegetable sampling event. Because there was no PFAS detected, there really aren't many results to discuss, but we can talk about what we found when we went out and we sampled. So we broke the vegetables and fruits into specific categories. These categories, essentially, it's either a root vegetable or it's an above ground vegetable. If it's an above ground vegetable, it's broken into categories based on whether or not it has a rind or skin that's removed or is eaten. These categories aren't very specific to PFAS. They're just convenient categories that are used in risk assessment. So we went with it, and if if we detected concentrations, we might rethink them. But in this case, these broad categories work okay, since we didn't have any detections in any case. But I will just talk through what we found. So on the top of this graph, we're showing the most frequently sampled type of vegetable, and that is also on the far left side of this little pictorial diagram. So these are exposed, what we call exposed vegetables, which just means you eat the skin. The skin is exposed to the air and you eat it. And that includes things like tomatoes, eggplants, peppers, summer squashes, cucumbers. I'm sure most gardeners have tried to or consistently grow many of these. Certainly tomatoes is one of the most commonly grown plants in New England, which falls into this category. And so, we found these on most properties and we sampled those most frequently. A subset of that is this dark green vegetable. So this is technically, it's an exposed vegetable, you eat the whole thing. But we pulled them out because the literature on PFAS uptake it's somewhat conflicting, but it suggests that uptake is likely to be more efficient for leaves of vegetables. So if there's anything that people are consuming, it's likely to be the leaf that may actually have the best chance, basically, for PFAS uptake. So we wanted to make sure that we collected as much dark green vegetable as we could in this sampling event. And as you can see, we got about 12 samples, which is roughly 1 per property. So if a resident was growing kale or lettuce, in some cases it was only things like sage and basil, which obviously you don't eat in as large a quantity, but they're still green plants. So we did collect those where we could. And then getting into the other categories where we didn't find nearly as many, there were a few fruits, not many root vegetables at all, only onions, and just the 1 butternut squash. Our sampling may have been a little bit early for the sorts of vegetables that would fall into that category. Butternuts, pumpkins, they don't tend to necessarily ripen until later, but we didn't note a lot of those being grown in the area. So we feel that this cross-section is pretty representative of what is being grown locally. And as we said, there was none of the 25 PFAS chemicals that were sampled for were detected in any of the fruits and vegetables. So moving on to pasture grass, just going through, I'll start on the right side of this figure. So as I said, there were 3 farms that we visited and collected samples from. We collected 8 pasture grass samples from each farm. We collected them in and out of active pasture areas, and we also collected them in and out of hydric soil areas. So when we go through the results, we're going to see that we collected pasture grass samples associated with dry soils and with hydric soils. And we did this based on that information about potential uptake into leaves. We thought there was a good chance there may be uptake in this pasture grass. So we wanted to bound it. We wanted to figure out if it was detected in this hydric soil, did it stop being detected on the edge of the hydric soil, and was it not detected in the dry soil? So So these 8 pasture grass samples per farm, they were really spread out between areas based on what the soil was like. So was it in or out of these hydric areas? And then we also gave some consideration to what the farmers were currently using. So are they currently using this pasture land? They want to make sure that that's safe for their cattle. So we took some samples that were specifically targeted for active pasture areas, as well as potential future pasture areas, and just testing out this whole conceptual pathway. So we sampled, as I said, multiple media. So we looked at the pasture grass, we also looked at hydric soil, we looked at dry soil, there was groundwater. And when we collected this groundwater, what we did is we essentially, we dug a little sump. So we basically dug a foot deep hole and let it fill in with groundwater. So if you can imagine, that groundwater is really, really shallow. It's just in that first foot. And so that's how that shallow groundwater sample was collected: sediment and surface water. And we didn't actually collect a dry soil sample. So it was hydric soil, groundwater, sediment, surface water, and pasture grass that were part of this sampling event. And just to go through the little bits in the arrow, this is a little reminder of what the conceptual model here. And I also want to mention that this data, when we look at this, so we have PFAS potentially in grass, water, and soil. And cattle, they do eat the grass. Obviously, they drink water. They also do eat some soil. So the way that we'll capture all of that is that we do have a risk model which can translate all 3 of those media into a potential concentration in meat. So that's where this all is going, once we get to the risk assessment phase. So if we look through the results, let's talk about the top row first. So we show our location and samples. So this is the sample number of pasture grass samples that were collected in dry soil for that top row. There were no PFAS detected, with one exception in these 12 samples. So that 12 samples is half of our sampling event. There were a total of 24 samples across the 3 farms. And out of that, for all 25 PFAS that we attempted to analyze for, we only found 1 detection. And unfortunately, as I said, we did not collect any co-located dry soil samples. So we don't have an immediate correlation for this sample. However, if you recall, last summer was a very wet summer. There was a lot of rain, and a lot of these areas, even though they're technically dry soil, were wet. They were wetter than they necessarily normally would be. And the shallow groundwater sample that was collected in the hydric soil sample that was on the same property did have PFBA in it. So that is one possibility. And so moving into the hydric soil, again, about half. So we had 11 samples that were collected of pasture grass that were collected on hydric soils. Again, no PFOS, no PFOA, no PFBS, none of the chemicals that we have toxicity data were detected, and no other PFAS were detected, with one exception. So in the hydric soils, we saw PFPEA detected in 2 samples out of these 11. And again, these are very low concentrations. I want to point out that they're J-flagged, which means that they're estimated values, that they're close to the limit of detection for the lab. So these are, considered low concentrations. And I also want to mention that we did have co-located soil samples for some of these. And what we found is that PFPEA was not detected in the soil, but it was detected in the shallow groundwater, which brings me to my last line. So we took 1 sample in a spring. So this grass sample was sitting in sediment in perennial water. So there's water there all year long. And we collected this sample on the advice of the resident, who suggested that the cattle have in the past and could in the future visit this spring, both for fresh water and also to eat grass in this area. So we collected this sample to see what the concentrations would be. And what we found is that we were seeing uptake in the grass in that 1 sample. So we had 6 PFAS detected in this 1 sample. And when you look at the co-located data, for one of our hydric soil samples and our sediment sample, we had exactly the same concentration of PFOS in the soil media, but we saw uptake into plants in the sediment, what we didn't see it in the hydric soil. So it suggests that that uptake could be coming more from the groundwater or from the water. So in the case of the spring, it's the surface water, which we know is impacted. So essentially what we're seeing is, we're possibly seeing that the water media is really driving any uptake. And I think that's also important to note that that's what essentially we're seeing in the literature. Again, some of the literature is very conflicting and it's hard to get a straight story. But what we find and what we've modeled in the past suggests that water is really the primary way that PFAS is taken up into plants. And that seems to be what these results are telling us. So just to recap what we've seen in the pasture grass, we did, as I said, we took into consideration what the active pasture areas were for these farmers and found no PFAS was detected in the pasture grass in those areas. The only place we did find PFOS and PFOA uptake, I should say, into grass was in that perennial spring sample, which is not currently being used for any purposes for cattle. And we did see that limited PFAS uptake in 3 of the pasture grass samples that were not in active pasture areas, but they were in the dry or the hydric soil locations. So, as with Hank's information, there's still analysis to be done, and we're figuring, we're figuring out how this will fit into the risk assessment process and where we go from here. And that's everything I wanted to cover today. So I think I will hand it back to Chris, who will go through what we're going to talk about next time.
Yes, thank you, Amy. So obviously from this presentation, everybody can see that this was a great deal of information, which is why we limited this to the groundwater results and also the backyard produce. So for the next RAB meeting, which will be in April, we will be talking about the remainder of the media. So soil, surface water, and sediment results, and along with the recent shellfish and freshwater fish and poultry egg results. So that should be a fun conversation as well. Next slide, please. There it goes. Okay, so obviously just a reminder of the remedial investigation timeline. It did start back in May of 2021, and it will be, phase 2 will be starting here shortly, and it's going to go into the fall of 2022. Administratively, we expect our draft RI report scheduled to be complete March 2023. All right, well, that brings us to the end. You can go to the next slide, but I just want to thank everybody who has participated in the making of this video. This has been an interesting process. Following this video, you at the same location where you've linked up to view this video, you can also find the tour of the Grafton Drinking Water Plant operated by the City of Portsmouth. We encourage you to check that out. And otherwise, we look forward to seeing you on the 28th of February, where we can discuss this video and any other data further. This will be a virtual RABs, and we hope to see you there. All right, good night, everybody. Thank you for attendance.